Welcome back, ladies and gentlemen. In this video we're going to be looking at some new ideas here related to angular position, velocity, and acceleration, obviously. But what we're really talking about is objects that are rotating. When we say angular, that's a reference to any object that's going to be rotating. And so from the beginning, it's very important to understand the difference between what we're talking about here with rotation as opposed to something moving in a circular pathway where you would say it is revolving. And when something is revolving, it's basically moving in a circular pathway, or nearly circular, as the orbits of the planets might be. But here now we're discussing rotation, something rotating, and we're going to be looking at how its position is changing as it rotates. And that would be an angular position. We're looking at how quickly it is rotating. That would be an angular velocity. And if the speed of rotation is changing, well, then there would be some angular acceleration taking place. So we're focusing here on rotation. But there are some connections to revolution, to objects moving in, say, a circular pathway, circular motion. So we'll see that come into play a little bit. First, let's look at this idea of angular position. How are we going to look at this? Angular position. Well, we're going to measure this as an angle theta, actually. And it's simply measured from some reference line. So if we have an object that's rotating, we can look at a wheel. Draw a quick circle here for us. And we have roughly the center, and so we can look at one spot on the rim of the wheel at the edge. There is, of course, a radius to this wheel, and what we can say then is, well, this spot right here is starting in this location. So we have a reference line, and that reference line is essentially just a starting point. That's all it is, and it can be anywhere we want. We could look at it with the reference line horizontal, and that's no big deal. We could look at it with the reference line vertical. It's essentially an arbitrary starting point where the angular position, where theta would be 0 at that reference line. And so if we have an object rotate, let's say we rotate the wheel some amount. Okay, so now that spot has a new angular position. And so what we can say is that now it's at that location, and it has rotated this way through some angle. Okay, that's easy to identify, right? But this angular position, so theta is just an angle measured from that reference line, but it's measured in radians. And that is simply because the using radians for our measure of this angle is going to be much more convenient for us than it would be to use degrees. But it's very easy to convert from degrees to radians, or the other way around also. There's something else going on here, though, and not only is there an angle going on, but there's an actual distance traveled. There's an arc length here. This arc length, S, just S for arc length. And when we look at this, we see this relationship with theta measured in radians. Then the arc length S is simply going to be equal to the radius of the circle times the angular change measured in radians. And the arc length S will have units of meters. And so we sort of are looking at, well, we changed position from here to here, and it rotated through a certain angle measured in radians, but it traveled through an arc length S measured in meters. Now there is also a sign convention, generally, and we're going to see this creep up as we go along here further. So conventionally, just basically what everybody agrees upon in terms of how to think of these things. When theta is greater than 0, as it's measured, then what we're looking at is counterclockwise rotation from the reference line. So wherever the reference line is, if we see a counterclockwise rotation, then theta will be positive. If we see a rotation that is clockwise, on the other hand, then the value of theta in this case would be negative. So theta will be negative or less than 0 when there is clockwise rotation from the reference line. And so we have to think about possibly completing a revolution, completing a rotation, or even going past a full rotation, but the direction matters. And so it might end up here, let's say it might end up here, and we might think, well, there was a certain amount of rotation in the positive direction, so theta would be positive. But if it was rotating this way and ended up there, then theta would have a negative value, and that will matter. That you can't just call it, I'm just going to call it the positive corresponding angle. No. It actually will matter. This counterclockwise versus clockwise difference really is critical to what we're going to be doing with rotating objects. Okay, so now we have position. Well, next thing would be displacement, and this is quite easy. Angular displacement. We're going to look at a change in theta, a change in the angular position. That's going to be your final minus your initial angular positions. Easy enough there, easy enough. Now the next thing to look at will be angular velocity. So what we're going to want to know is, well, if the angular position is changing, if we're experiencing an angular displacement, how quickly is that happening, right? So here we go. Angular velocity will simply be the rate of change of angular position. And we will give this a symbol omega, lowercase omega, and we're going to say that the average rate of change of angular position, or in other words, angular velocity, is going to be the change in position divided by some time interval. Easy enough. The rate of change of angular position. Now, if we wanted the instantaneous, we would say that the instantaneous angular velocity is simply the limit as delta t goes to 0 of this relationship. And we might want to look at that at some point, because we will have changing angular velocity as well. Therefore, it's going to be an angular acceleration taking place. But if you look at this, we say that the angular velocity can be positive or negative. And that direction actually is critical. So this truly is a velocity, although there is such a thing as angular speed as well. And the symbol for angular speed is identical. It's still a lowercase omega. What you'll have to do is look at the context of the situation and try to decide, is it angular velocity or angular speed? And so will the sign matter? It depends on the context, depends on the particular thing you're working on. Well, here the sign convention Again, it's pretty straightforward. So omega will be positive, will be greater than 0 with any counterclockwise rotation. And omega will be less than 0 or negative with any clockwise rotation. So, okay, please don't get fooled. That's not an omega, that's a W. That's just how I write my W's. So, counterclockwise versus clockwise rotation. So we can see that. I can show you that real quick here. And so if we have counterclockwise rotation, there's counterclockwise, then omega, I'm sorry, I shouldn't say omega, I really should say angular velocity. Angular velocity will be positive. On the other hand, if we have clockwise rotation, angular velocity will be negative. And this is kind of interesting because if you imagine, well, we're viewing this from one side of the wheel, if we're using a wheel as our example, right? Oh, what about somebody on the other side of the wheel? They would actually view this direction of rotation right here. To them, that would be clockwise rotation. If you imagine flipping this over, taking this and kind of looking at the back side. And so, yes, your perspective totally matters. And you would just have to deal with that appropriately. Should not be too much of an issue for you. Now, what I want to look at, though, is how much time would be needed to complete one revolution. So at a certain angular velocity, how much time is needed for one complete, I said revolution, didn't I? One complete rotation. And so one complete rotation, when we figure this out, we're going to have a reference line in there. And from the center, centered about there maybe, let's just put a reference line there. And that's where theta would be 0. And we're going to complete one full rotation. So there's theta. So essentially, well, really it's our change in theta, isn't it? We started at 0, we ended at 0. But there's another way of looking at that. So if we want a time, then we're going to have to figure out a total change in our angular position. Well, if it goes once around, then its change in angular position is going to be 2 pi radians. Right? So 2 pi really is the quantity. And radians, you think of this as our unit, but it really is a dimensionless quantity. So being dimensionless, that's going to possibly throw you off with some of the units of things later on. Don't let it throw you off. Just stay focused and you're going to be okay. Well, there is our essentially our distance traveled, and we're going to look at a time interval. Well, for this time interval for once around, that is defined as the period of rotation, capital T, when we're dealing stuff like this with, dealing with stuff like this. Capital T is the period of rotation. By definition, the length of time needed for one full rotation. So from these two quantities, we can say that, well, since the angular velocity is equal to this relationship, the essentially angular displacement divided by the time interval, we can do a substitution. We say, well, no, sorry, not delta. Substitution would be, well, this is 2 pi, and this is the period, capital T. And when we solve this for the period for one rotation, then we essentially get 2 pi divided by the angular velocity. This is how you'd figure out how long it's going to take to complete one rotation. You would simply have to say, well, the one rotation is going to be 2 pi around the circle, measured in radians, and we need to know how fast it's going in terms of an angular velocity. So that's going to be a nice important relationship to remember. Put a box around that for you. Simple, but you'll want to know that one. Now, oh, you know what? Let me put a box around this guy as well. You definitely need to know that relationship also. And I mentioned earlier, well, there's the possibility of changing this angular velocity. So if we get this thing rotating, say counterclockwise, then it had to start from 0 angular velocity, and we got it to some angular velocity. Therefore, there's an acceleration. And this acceleration is an angular quantity all over again. So let's look at that. Angular acceleration. The symbol here is going to be alpha. Physicists love our Greek letters, right? So essentially, since it's an acceleration, it is the rate of change of angular velocity of omega. That is essentially what's going on here. So we're going to be able to say, well, the average angular acceleration, therefore, is equal to the rate of change of angular velocity. The units here are simply radians per second squared. You know what? I should probably throw that in here as well for angular velocity. The units, ITS, I can spell, will be radians per second for angular velocity. And here the units for angular acceleration, units are radians per second squared. Should look very familiar, just like it is with linear acceleration. And of course, I'm going to throw this in here in case it ever comes up. The instantaneous angular velocity, well, I want to look at the limit as delta t approaches 0 of your change in angular velocity divided by the time interval. Not an equation we're going to be using much. It essentially is going to boil down to the average, and you'll see why later on. Now there is a sign convention here as well. And it's essentially this. If your angular velocity is becoming more positive, then your angular acceleration is positive. No big surprise there. And conversely, if your angular velocity is becoming more negative, then your angular acceleration is negative. Those are sentences. Another way of saying this part right here, if angular velocity is becoming more positive or more negative, well, you can simply look at the change in angular velocity. If it is a positive change or a negative change. And that would indicate a positive angular acceleration or a negative angular acceleration accordingly, right? So here's something else to think about. If the angular velocity and the angular acceleration have the same sign, then what's going to happen to the speed of rotation? If they have the same sign, then the speed of rotation increases. It speeds up. Well, think back to when we were studying linear motion. If the velocity and the acceleration have the same sign, the object, maybe it's a car, the car would be speeding up. If the velocity and the acceleration have opposite signs, then the car would be slowing down. Same thing is happening here. So the converse of this is also true. So if angular velocity and angular acceleration have opposite signs, then the rotation then the speed of rotation will decrease. Rotational speed will slow down. All right. So a couple important points to always keep in mind. You know, because this relates to the physical situation that's happening, and you never want to lose sight of that. All right. So now, what you probably are thinking in your head, and you should be, is that there's a whole lot going on here with angular motion that seems very, very familiar, very similar to all the linear stuff we learned earlier. And you'd be very correct in saying that. And in fact, I need you thinking like that. So to help out, what we're going to do is basically outline all the equations from linear motion and look at their counterparts for rotational motion, essentially looking at rotational kinematics, all those equations of motion. So the equations for linear motion, for example, velocity is equal to initial velocity plus acceleration times time, and all the others, right? All the others. So all those equations of motion, the kinematics equations, they worked only when acceleration was constant. If the rate of acceleration was varying, well, those equations were just not applicable. They just wouldn't work for you. We're going to see something just like that here, and we're going to develop a set of equations for rotational motion. But they must be used for situations where the angular acceleration is constant. For example, so we're going to look at this relationship here. Angular acceleration is the change in angular velocity divided by time interval. So we can rewrite this a little bit. We can say, well, this delta omega is equal to really your change in angular velocity is final minus initial angular velocity. When we do this, we typically are going to start counting at time 0, so your time minus your initial time would be 0. And this simplifies a little bit. Just have to write a time. And what's going to be neat is solving for the final angular velocity. We're going to see initial plus, remember this is equal to that guy, so I'm just basically going to have the counterpart of that equation right there. Where this is for linear motion, this will be working for angular motion, rotational motion, right? So here are the equations coming up your way. I'm going to start a new sheet of paper because there's actually quite a bit to write. Now, if you would prefer to not rewrite all of these kinematics equations, you certainly don't have to. But I'm going to lay them out, and in fact, I'm going to lay them out in a way where we're looking at a couple of them in a couple different ways. So we will have linear equations of motion. And remember, this must be for constant acceleration. And we're going to correspondingly have rotational equations of motion, but we must have not an x, constant alpha, constant angular acceleration here. So T, and then the way your book writes this next one, I'm not super crazy about the form. I'll show you what I would prefer, but I mean what I would prefer. I should say what I like to use better. The form of the equation that you decide to use was completely up to you. I don't have a preference in terms of how you write the equation as long as it is correct. So to me this is an interesting way of looking at it, and there's a couple other alternatives here. Let me show you those real quick. I'll change colors so they maybe don't get too confused. You could say, well, subtract initial from both sides, and I'm basically talking about my change in position. And so I just get 1/2 initial plus final times t. Well, initial plus final divided by 2 is really your average velocity, right? Average velocity times time is your change in position. So really this equation boils down to this. So I'm going to put this in sort of a bracket and separate it off. These two are just this equation right here rewritten. Now there's another one, of course. We have your final position is equal to your initial position plus initial velocity times time plus 1/2 acceleration times time squared. Okay, that should look familiar. Sort of the same thing. I'm sort of used to taking this over here and writing a change in position on one side. No big deal. And one more important one, final velocity squared is equal to initial velocity squared plus 2 times acceleration times the difference in positions. So like before, I'm used to simply writing a delta x instead of that, but that's fine. That's fine. So we have these four important, 4 important equations. Those are not minus signs. Those are just sort of identifying the important equations of kinematics here. We have a corresponding equation for rotational motion for each of these. So here we go. You already saw this one. Final angular velocity equals initial angular velocity plus angular acceleration times time. This next one, well, all we're doing is substituting our angular quantity for each of these linear quantities. That's really it. So we have a final angular position equals initial angular position plus 1/2 initial plus final angular velocities times time. And just like before, there's other ways I like to do this. Changing angular position is one way. And of course, this is just the average angular velocity. So you saw that equation previously, so I'm going to put these in brackets. This is not separate equations. They're just sort of looking at this one in a different way, rearranging. But there's more. We have final angular position equals initial angular position plus initial angular velocity times time plus 1/2 angular acceleration. Don't let that look like an x. Times squared. Again, instead of doing this and separating it, oftentimes I will just write that, and that's fine. Finally, we have, did I miss one? What did I do? Oh, okay. Finally, we have, sorry, I was examining my own notes. Final angular velocity equals initial angular velocity squared on both, plus 2 times angular acceleration times the differences in those angular positions. And I'm used to just doing change like that. Okay, so equations that you don't have to memorize, but you're gonna use them so much you probably will end up memorizing them. So we have 1, 2, 3, and 4, with a couple different forms of some of them. Not a problem. And of course, you guys are really good at math, so rearranging these things is no big deal. Well, I'm gonna shut this one down. And we're going to, in the next video, it's going to be a supplement to this one. We're going to examine some connections between the linear quantities and the rotational quantities. Thanks for watching. I'll see you next time.